Welcome to Ask and Learn.
Here is an example of a Carnot heat engine cycle using an ideal gas. So a reminder that a Carnot engine has two isothermal processes, one an expansion, one a contraction. During the expansion at high temperature, heat is absorbed. During the contraction, heat is expelled to the cold reservoir at low temperature. Then there are two adiabatic processes where heat does not have a chance to exchange with the environment. One is, again, a contraction. One, again, is an expansion. Usually when analyzing these cycles, a couple of tools are helpful. One is the ideal gas law, provided an ideal gas is used. So I usually like to write that down and then find the pressure and volume and temperature at each of the four vertices shown in the cycle. The other tool that often is useful is the first law of thermodynamics. Delta U is equal to Q, heat, minus work done by the engine. That could be helpful. For processes or cycles that involve adiabatic processes, it is also good to realize that pressure times volume raised to the adiabatic exponent is equal to a constant. A reminder that the adiabatic exponent is a ratio of Cp to Cv and depends on the nature of the gas. Here, we are given that this constant is 1.3. So this is usually how I like to start. I usually like to start with a table and fill out the three state variables, pressure, volume, and temperature, for each of the vertices in the cycle. Here there are four that are labeled in the diagram for us. Now, this problem is challenging because they don't give us outright numbers, but they provide clues as to what's going on with this particular sample, to put it mildly. And so the first thing they tell us is that there's the ambient environment that the particle is interacting with at 0.4. And they give us the ambient temperature as 123 Kelvin. Now that's good because we now know the temperature at 0.1 because of the isothermal process. They also tell us that we are at 1 atmosphere at that point, but they don't tell us what 1 atmosphere is, other than, it's ambient there. Some other clues: at 0.1, we are told there's something called the trigger volume. And that's going to become important because at 0.2, we get squeezed to half the trigger volume with the radius given as 0.08 centimeters. That's kind of cubes. That's kind of, no, not cubed, sorry. Yeah, that's kind of a weird way to give a clue. But at 0.2, they also give us the pressure as 20.3 kilopascals. So that's an outright calibrated measurement. Kilopascals. At 0.3, they give us the clue that, no, it's actually at 0.4, they give us the clue that the final radius expands from the trigger radius by 3. And since volume is r cubed, that tells us that we have 27 times the trigger volume. So we have some clues, and I think these are the most obvious clues. The rest we're going to have to use some steps with the gas law and the adiabatic exponent to figure out. So looking at the table, the most information appears to be given, well, we'll start with 2 because there's a nice calibrated point right there. And so at point 2, what we know is the volume is 4/3 pi r cubed. And that's going to unravel a lot. So we have 2.14 times 10 to the minus 3 cubic meters. Figuring that out, I won't show all the math there. And then what happens is we can now find the trigger volume by just multiplying it by 2. And that will give us the entry for the volume at point 1. And it will also give us then the volume at point 4, which is 27 times that, which is 0.116 cubic meters. And we can fill in that entry into the table. So now we've got to do a little bit more work. We see that there's quite a bit of information given in steps 1 and 2, and they are connected through an adiabatic process. So what we can do between 1 and 2, because it is adiabatic, we can set the pressure 1 times the volume 1 raised to 1.3 is equal to the pressure at point 2 times the volume at 2 raised to the 1.3. And let's see, that is going to give us, of the unknowns, it will give us the pressure at point 1. So we can solve for that, and we get 8.24 kilopascals. And bingo, now we've got everything inside of point 1. We've got, yeah, definitely a bingo type situation. Everything is filled in. So we can now use 1, that everything in that point, to solve for the number of moles. R is just the gas constant, 8.31 joules per mole Kelvin. And we could solve for that high temperature, which is a very important quantity once we find the number of moles. Okay, but actually we're using that point to solve for the number of moles, so let me be clear about that. Okay, so we can solve for the number of moles. And that's definitely important quantity, 3.45 times 10 to the minus 2 moles, which I'll just write off to the side because that is an important clue that we can then use in point 2 to find the high temperature. it's like a mystery that unravels. And doing that, again, I won't show all the plugging and chugging, but we get a temperature of 151.5 Kelvin. And that's nice because we now know both the low temperature and the high temperature. And that is definitely important things for the operation of a Carnot cycle. But while we're at it, we have a few more things to fill out, so we might as well go ahead and fill those out. There's a lot of information missing at point 3, and as well as point 4. But what we see is point 3 is connected to point 4 through a adiabatic. So let's stop with one more step. What about point 3? It's connected to 4 through adiabatic, and it's connected to 2 through isothermal. So what we can say is the following two relationships. The unknown pressure at 3 times the unknown volume at 3 raised to 1.3, that adiabatic exponent, is equal to pressure at 4, volume at 4, raised to the 1.3. Okay. Well, we don't know pressure at 4, do we? But we can use the fact that 4 is connected to 1 through an isotherm. And so we can say that pressure 4, volume 4, is equal to pressure 1, volume 1. And we definitely know both of those at point 1. And we also know the volume at point 4. So we can solve for pressure 4. And again, I'll spare the details, but we basically get 301 pascals. Okay, now what do we know? We don't know either pressure 3 or volume 3, so we have to connect it to point 2 through the isotherm. Okay, so we know both pressure volume at point 4, same with 2. We have 2 equations and 2 unknowns. And we can definitely then solve for both pressure 3 and volume 3. And what are the steps to that? Well, I would probably take the bottom relationship and solve it for pressure 3. And put that back into the top equation. Yeah, 1.3 is the exponent. And solving that, we get volume 3 is equal to 5.84 times 10 to the minus 2 cubic meters, and then we can solve for pressure 3. Okay, so yeah, we've got the table full at this point. So I'll put a little face by that to show that that one is the most challenging. And it's probably the least interesting too on top of it. So at this point, we have all the information about this cycle. We can do some other things with the cycle, basically knowing what the Carnot efficiency is. I will use the expression without the percentage because certainly getting the fraction is good enough. But that efficiency is basically the difference between the high and the low temperature divided by the high temperature. So we know both of these temperatures, and we can figure out that efficiency. It's about 18.8%, but 0.188 in terms of a fraction. And a reminder that any engine has another definition of efficiency, is the work that you get out divided by the heat absorbed at high temperature during the high temperature isothermal expansion. So yes, while the gas is heating up, it is expanding and pushing against something, whether it's the wheels, the shaft of your car with a piston that's pushing, or whether it's this little particle doing something, expanding. Anyway, what we're told is that the work out is 60 kilojoules per hour. And that's really a rate at which work is being done. 60 kilojoules per hour is the same as 1 kilojoule per minute. Just thinking about how hours translate to minutes. And then we can figure out the heat that is absorbed, at least the rate. Just turning those into rates does not change the fraction there. And so QH dot, the rate at which heat is absorbed, is simply 5.32 kilojoules per minute. And then we want to use the first law to figure out the difference between the heat absorbed minus the heat expelled, exhaust heat, is equal to the output work. And really what you're doing with that is using the first law with delta U equals to 0. And solving for QC dot. It's the heat absorbed minus the output work. Energy must be conserved. And so this is 4.32 kilojoules per minute.